Welcome back to the deep dive, you brilliant and incredibly curious person.
Hello there.
Today, we are taking a trip. A big one. 1.3 billion light years away, to be exact.
And the sources you sent us are... they're just fantastic. We've got academic papers, some technical preprints from the LVK collaboration, computational physics notes. It's a lot.
It is, and they all tell a story that is, frankly, astounding. A real validation of a century of physics.
Well, it's more than a story.
Right.
It's a confirmation.
We're looking at one single cosmic event, a gravitational wave signal so clear, so profoundly loud, that it let scientists run the ultimate diagnostic check.
On who, exactly?
On the two biggest laws we have for black holes, the predictions of Albert Einstein's general relativity and Stephen Hawking's foundational theorem on black hole thermodynamics, both tested at once.
And that is precisely our mission today. We are unpacking the significance and the shock waves, both literal and figurative, of the gravitational wave signal, known as GW250114.
Yeah, this wasn't just another discovery in a long line of them.
Not at all. This was a statistical jackpot. It gave us the most stringent one-shot confirmation yet that black holes are exactly what our most advanced theories predicted them to be.
So we need to get into why this one signal changed the whole game.
Exactly. It moved the entire conversation from, do these laws actually hold up, to...
Okay, they hold up perfectly. So what in the universe will it finally take to break them?
That's the transition, and it's the core of this deep dive.
Before this, we were, piecing together evidence from dozens of faint whispers.
Faint whispers is a good way to put it,
Yeah.
yeah. GW250114 wasn't a whisper, it was a sonic boom.
And we're going to explore how that incredible clarity allowed physicists to test the ring-down phase of the merger.
Which is exactly where general relativity is most vulnerable, most likely to be proven wrong.
And at the same time, how they checked Hawking's area law with a precision that was, until now, just unimaginable.
Okay, let's do it.
All right, let's set the scene. I want you to picture this. It's January 14, 2025. Think about the LIGO detector facilities. One in Hanford, Washington, one in Livingston, Louisiana. These are not bustling labs full of people in white coats.
No, they're incredibly isolated. They have to be.
They're quiet, enormous buildings. And inside, they're hosting these vacuum tubes that are 4 kilometers long.
Just massive structure.
And inside those tubes, mirrors, about the size of dinner plates, are hanging, just perfectly suspended, hypersensitive to any motion at all.
It's so important to really visualize the scale of
That isolation, I mean, they're trying to measure the physical distortion of space-time itself.
Right.
So they have to ignore everything else. All seismic noise, cars driving miles away,
human activity, weather.
Everything.
They're trying to listen to the very structure of the universe changing, and that requires a kind of silence that is just phenomenal.
They were silent sentinels, waiting for a disturbance that might move them less than 1/10,000th the width of a single proton.
An impossible measurement, really.
And on that quiet Tuesday in January, something arrived. It wasn't light, it wasn't radiation, it was a physical ripple, a traveling distortion in the very fabric of space-time.
Classified way.
The collision of two gargantuan black holes, 1.3 billion light years away.
Wow.
And when this wave washed over those detectors, it didn't register as a faint chirp or a whisper like the others. The sources describe it as an explosive, clear thump.
Okay, hold on a second. A thump.
A thump.
From 1.3 billion light years away. I mean, that distance is, it's practically unimaginable.
That is.
When you think about the vastness of the universe and how much
Energy must dissipate over that kind of cosmological travel time. I mean, most signals we detect are statistical ghosts.
Right? You have to know where to look.
Exactly. They're signals we only find because we know exactly where and when to look, and then we average out all the noise over time to see the faint trace. How could a signal from that far away be loud?
That is the hook. And it all comes down to one number. It's the signal-to-noise ratio, or, SNR. Now, the energy released by the black hole collision itself was enormous, of course. A huge amount of mass was just converted directly into gravitational waves. But the real game changer here is how cleanly the detector captured it against its own background noise.
So the SNR is the clarity metric.
Exactly.
It's like, okay, it's like trying to listen to someone telling you a vital piece of information during a really loud party.
Good analogy.
If the person speaking is just, a little bit louder than the crowd, your SNR is low, you have to keep
asking them to repeat themselves. You're straining to get the message.
Right. And with GW250114, the static, the party noise, was just completely drowned out by the message.
So it was a clear
voice.
The source is really clear on this. The prior gold standard, the best one they had before this, was a signal signal called GW250114.
And that one was already considered a big deal.
Oh yeah, it had an impressive SNR of 42 that was considered a superb, clean catch. Got a very clear voice in the room.
Okay, an SNR of 42, that's already providing really rich data. So what did GW250114 actually clock in at?
The network matched filter SNR for GW250114 point hit an astonishing 77 to 80. 80.
Wait, okay, I'm pausing here because for anyone who works with data, that number is just, it's staggering.
Right.
That is not just incrementally better. That is roughly 4 times clearer than the previous record. This is a fundamental leap in data quality. It's not a step, it's a jump.
It is a massive jump. And the reason that move from 42 to 80 is so important is all about the statistics. The uncertainty
In your measurement, it scales inversely with the SNR.
Mm-hmm.
So when you more than double the SNR, you roughly quadruple the precision with which you can measure the physical
parameters of the black hole. Things like its mass, its spin, its vibrational frequency.
So you're saying that error bars, the uncertainty, just shrink by a factor of 4?
That's it.
Which means we're moving from, we think this is what happened, to we can measure the properties of that final black hole with crystalline certainty.
Precisely. This clarity transforms the whole observation. It's no longer a statistical inference where you have to use immense computational power to filter out the hum.
Right?
It becomes what the sources call an undeniable direct eavesdrop on the universe's most violent events.
I like that. An eavesdrop.
We didn't just hear the crash, we heard the resulting bell tone perfectly. And that perfect tone is what allowed us to test fundamental physics.
Which was desperately needed.
Desperately. I mean, for decades, we had to rely on indirect measurements to try and prove general relativity's predictions about black holes.
Plus, you can't see them.
Right. They're invisible by definition.
And the best historical evidence we had, before we detected these waves directly in 2015, was incredible, but it was still indirect. I'm talking about the Hulse-Taylor binary pulsar system.
Ah, yes, the 1993 Nobel Prize winner. We should probably elaborate on that, just for context.
Definitely. So Russell Hulse and Joseph Taylor, they tracked the orbits of 2 neutron stars revolving around each other, like 2 incredibly dense spinning tops.
And what they found was that the system was losing energy. The 2 stars were getting closer and closer together. Their orbital period was shrinking.
Right. And they tracked this orbital decay over years. And the rate of energy loss, it matched Einstein's general relativity prediction for the emission of gravitational waves. Perfectly. It was one of the most stunning confirmations in the history of science.
It was empirical proof that the math was correct, but we still hadn't seen the waves themselves.
Right.
It's like proving an earthquake happened by measuring how the landscape tilted weeks later. You know it happened, but you never felt the tremor or saw the seismograph spike.
Great analogy.
The 2015 detection finally gave us that tremor. But as we said, those early signals, with their low SNR, they only confirmed the broad strokes.
That black holes merge and they create gravitational waves, the basics.
Exactly. They didn't let us confirm the fine print, the really detailed geometry and behavior of the resulting black hole.
And that fine print involves 2 of the absolute titans of 20th century physics. Einstein and Hawking. We had to test their theories where the physics are most extreme.
So let's start with the first theoretical giant on the line. Einstein's general relativity, and specifically how it relates to something called the Kerr metric.
The Kerr metric. So for any listener who knows the concept but needs the deep dive context, this is the perfect, simple mathematical description of a rotating black hole. Roy Kerr discovered it
back in 1963.
And it's so important because according to general relativity, and this famous idea called the no-hair theorem.
Which is a great name.
It is a great name. It says that any object that
collapses into a black hole, doesn't matter if it was a chaotic star or 2 merging black holes, it has to immediately settle into a state that's defined only by its mass and its spin.
That's it, just 2 numbers.
Just 2. Yeah. All the other hair, all the complexity of its formation, the bumps, the lumps, it all has to be radiated away, gone.
Okay, that is a huge claim. It's saying that this final merged black hole, born from just immense violence, has to instantly become this simple, perfect, mathematically defined object. So the challenge for physicists is, how do you test that rapid transformation?
You test it during the Ringdown phase. That's the final fractions of a second when the newly formed black hole is literally vibrating like a struck bell before it settles into its stable Kerr state.
And if general relativity is correct,
And those vibrations, those notes, they have to be predicted precisely by the current metric.
So if the measured frequencies and the decay rates of those notes, which are the gravitational waves we detect, if they deviate
even slightly from what the current metric predicts,
then general relativity fails in this high-velocity, strong gravity regime, and we need new physics. The whole thing comes into question.
Okay, massive stakes there. So now let's bring in the second giant. Hawking's area law from 1971.
Just as crucial, this is the law that links gravity and thermodynamics.
And it's a simple statement. It says that the total surface area of a black hole's event horizon, or event horizons if you have more than one, it can never decrease.
never.
It must always stay the same or increase.
Yeah.
This is basically treated as the second law of black hole mechanics. It's an analog to the second law of thermodynamics, where entropy always has to increase.
But this is where the stakes get really high again, because why is this so hard to prove? Why is it even a paradox during a merger?
It's because of the massive chaotic energy dynamics. I mean, when two black holes merge, they radiate an insane amount of energy away as gravitational waves.
Right. And massive energy loss should correspond to mass loss. And mass loss should mean a smaller event horizon. Simple enough.
You'd think so. And on top of that, you mentioned the spin. When the remnant black hole forms, it often spins much faster than the two black holes that created it.
And a faster spinning black hole, relative to a non-spinning one of the same mass, actually has a smaller event horizon area.
Exactly. So you've got two different physical processes, energy radiation and increased spin, that are both working against an area increase.
And yet,
Hawking's law demands that the final total area must be larger than the initial combined area of the two black holes.
so if the signals weren't clear enough to measure the masses and spins really accurately, you couldn't calculate the initial and final areas. And the law would just remain an unconfirmed theory in this kind of violent scenario.
That's the problem they had. To verify Hawking, you need exquisite fidelity on all four parameters, the two initial masses and spins, and the final mass and spin. And that's why GW250114 was the perfect instrument for the job.
So how do you actually do it? How do you manage the physics and the data analysis to prove these two titans right?
It takes a scale of cooperation that is almost unbelievable. We're talking about the LVK collaboration. That's LIGO, Virgo, and K-Graia, a global network of detectors and over 1,600 scientists collaborating across different continents.
It's this monumental global effort, but the sources we looked at, they really emphasize the crucial foundational role of the computational infrastructure.
The supercomputers.
Exactly. For instance, the gravity group at Penn State wasn't just observing, they were developing the very architecture needed to process all this data. They built this massive ICDS supercomputer cluster.
We should spend a minute on that computational side, because it really is the unsung hero here.
I agree.
We talk about the detectors, but the data processing is
Is arguably even harder. The LVK detectors produce raw data at truly astronomical rates.
A fire hose of data.
And to filter out that tiny gravitational wave
wave signal from all the background noise, thermal, seismic, electronic. They use these incredibly complex algorithms.
They use a technique called matched filtering.
Right. Can you break that down?
Sure. Think of it like a digital sieve, or maybe a key that fits a very specific lock. The scientists create a huge bank of millions of theoretical waveforms templates of what a gravitational wave signal should look like, based on general relativity's predictions for every possible black hole mass and spin combination.
Okay, so they have a library of all possible sounds.
A massive library, and when the raw detector data streams in, they run it through all of these templates, looking for a perfect match, a signal that
Fits one of those theoretical keys perfectly.
And that computational feat must require ridiculous speed.
It does. When GW250114 arrived, that ICDS
supercomputer cluster had to process the data in near real time to identify the statistical match.
And confirm it was multiple detectors, right? LIGO and Virgo were operating at the time.
Yes, and then send out an alert to astronomers around the world. The sources suggest that the rapid confirmation of GW250114, even with its phenomenal SNR, required these specialized search pipelines that Penn State and other groups have developed.
It's just amazing how much the detection capability has improved.
It's staggering. We went from struggling to identify just a handful of signals in the early days of LIGO to the current 04 observing run.
Where they're now catching a merger roughly once every 3 days.
Every 3 days. But GW250112 just stands alone. Its clarity meant the match filter template didn't have to strain at all. It was an undeniable immediate fit, a perfect key and a perfect lock.
Okay, so let's pivot from the computational side to the core physical measurement. black hole spectroscopy. We need to go back to that struck bell.
This is where we get to test the Kerr metric and that no-hair theorem. And the analogy is perfect, but we need to dive into the physics of the sound.
Right. So when the two black holes merge, the new object is highly distorted. It's not a perfect sphere yet, it's wobbling.
And it violently settles back into that simple, stable Kerr shape.
I'm picturing a massive drop of water that just had another drop splash into it. It oscillates wildly for a moment before it forms a new, stable sphere.
That's a great visual. And during those oscillations, the black hole is emitting the gravitational waves that we call the ringdown.
And these oscillations, these ringdown tones, are what physicists call Quasi-Normal Modes, or QNMs.
Right. And just like striking a large bell, you don't just get one sound. You get the main loud tone, the fundamental note, but then you also get these fainter, higher pitched, more rapidly decaying secondary notes, the overtones.
And here's the kicker. The Kerr metric dictates the exact properties of all of these QNMs.
All of them.
If you know the final mass and the final spin of the new black hole, general relativity tells you the precise frequency, the pitch, and the damping time, how quickly the sound fades, for every single one of those QNMs.
So if the newly formed black hole is truly a Kerr black hole, its entire vibrational signature has to be consistent.
Exactly.
Measuring just the loudest tone isn't enough to prove the no-hair theorem, right? Because many non-Kerr objects could potentially ring out a similar loud tone.
You're one step ahead. That's exactly right. You need to hear the subtle echoes, the overtones. And GW250114 was the first time scientists could clearly distinguish and measure these specific overtones simply because the signal-to-noise ratio was so incredibly high.
Okay, so tell us about these notes. What did they hear?
So they decomposed the signal, and they identified two crucial notes in that post-merger data. First, the dominant fundamental tone.
The big word.
That's the quadrupolar mode, which is labeled the M2 and $QNM. They often just simplify that to the 220 QNM.
Okay, 220.
That's the loudest, longest-lasting part of the sound, the main ring of the bell.
And the 220 mode is the basic stretch and squeeze of space-time that we usually think of.
Correct. But the real scientific meat, the thing that got everyone excited, was the secondary, rapidly decaying tone. The first overtone. They call it the 221 QNM.
And this one fades much faster than the fundamental.
Much faster.
Why? Why does the 221 decay faster? What does that physics tell us?
The rate of decay is directly linked to how quickly the gravitational perturbation is damped out and sort of absorbed by the event horizon.
The 221 mode represents a more complex, less symmetric distortion of the black hole. And since the black hole is trying to settle into the simplest possible Kerr state, it sheds that complex hair, the 221 mode, much faster than it sheds the fundamental, simple 220 mode.
Okay, so this is why it's the ultimate test. General relativity says the final black hole should only have two numbers defining it, mass and spin.
Right.
So if you calculate the mass and spin required to produce the 220
Frequency that you measured.
Yep.
And then you independently use those exact same mass and spin numbers to predict the frequency and the decay time of the 221 overtone. They
absolutely have to match what you measured for the overtone.
Perfectly. If they don't, something is wrong. If the 220 note suggested a mass of, say, 60 solar masses, but the 221 note suggested 65 solar masses,
and the Kerr metric would be invalidated and the no-hair theorem would collapse. The whole thing falls apart.
The consistency across these different vibrational modes is the smoking gun for Einstein's perfection.
And with GW250114 being so clear, I read they went even further down the rabbit hole.
They did. For the first time, they were able to constrain the frequency of a tertiary subdominant tone.
A third note.
A third note. The hexagacopolar mode, the MBR. They call it the 440 QNM.
Okay, that sounds incredibly complex.
It is. This mode is incredibly quiet and represents a much higher order geometric distortion of the black hole shape. Just measuring it at all means you're probing the inner structure of that newly formed black hole with phenomenal depth.
Wow. Okay, so let's get to the discovery
itself. What were the actual parameters of this merger that made the test so perfect?
The sources revealed that the two merging black holes were near equal in mass, which is a key detail.
One was 33.6 times the mass of our sun, and the other was 32.2 times the mass of the sun.
So they were almost twins.
Pretty much. And crucially, they had very small initial spins and negligible eccentricity, meaning their orbits were almost perfect circles.
Okay, so I have to challenge this a little bit. That's an important detail. If the black holes were near twins with low spin, isn't that the easiest possible scenario for general relativity to pass?
That's a fair point.
It's the closest you can get to a perfectly symmetric collision. Shouldn't we wait for a really high spin, highly eccentric, messy merger before we declare total victory for Einstein?
It's a really good question, and the sources address this. They confirm that yes, while it's a clean event, the sheer precision they achieved here is what matters, regardless of the symmetry.
So the clarity trumps the messiness.
Exactly. The high SNR allowed them to measure any hypothetical deviation with the maximum possible sensitivity.
So yeah, it passed the easiest test, but it passed it with the tightest possible constraints. Any deviation, even a tiny, tiny one, would have been visible.
Okay, I'll buy that. So let's look at Vindication 1.
Einstein's perfect pitch. What was the quantifiable result of hearing that perfect tone?
Measured Q&M frequencies and damping times for both the 220 fundamental and the 221 overtone. They agreed with the predictions of general relativity to within a few percent.
A few percent, that's already incredible.
But get this, the constraints they placed on the dominant 220 Q&M frequency were twice as stringent as the combined constraints they got from hierarchically analyzing dozens of previous fainter events compiled in the big GWTC 4.0 catalog.
Wait, just stop there. I need to dwell on that statistic because that is a scientific mic drop.
It really is.
You were telling me that one single 0.2-second event, this GW250114, provided a better, more
Precise test of the Kerr metric than the combined average results of the 17 loudest events they had ever recorded up until that point.
That is exactly what the sources confirm. This single event represents
An order of magnitude increase in measurement efficiency.
Dang.
I mean, there's all those low SNR signals. While they were historically important for getting us here, they're now scientifically less useful for testing the detailed structure of gravity compared to just waiting for a single perfect catch like this one.
It validates the entire methodology of black hole spectroscopy.
It verifies that the structure of the remnant black hole is exactly what the no-hair theorem demands. It's defined only by mass and spin. And this perfection extended to those fainter notes too, right?
yes, the 440 QNM. For the very first time, they were able to constrain the frequency of that quiet, high-order geometric distortion.
Mm-hmm.
And it, too, was consistent with the GR prediction. Now, the uncertainty margins were wider than for the dominant modes, of course.
Sure, that makes sense.
But the fact they could measure it at L validates all the analytical techniques that the LVK teams have been developing for years.
Mind-blowing. Okay, so let's move to Vindication 2. Hawking was right, the area law. This is a measure of black hole thermodynamics. Does the total surface area actually increase during a collision?
And this all relies on the same precise mass and spin measurements they got from the ringdown and the in-spiral phases.
Right. If those measurements are fuzzy, the area calculation is basically worthless. But since the measurements here were crystal clear, the area test became definitive.
Let's use that scaled comparison from the sources to really grasp the magnitude. Before the merger, the two black holes had a combined event horizon area of approximately 240,000 square kilometers.
Hey, 240,000. To put that into perspective for people, that's roughly the size of the United Kingdom.
A good comparison.
Yeah,
Or a little less than the state of Michigan.
right.
After the merger, the resulting single black hole settled down. And despite the enormous energy that was radiated away, about 3.5 solar masses of pure energy just lost to the cosmos.
The final event horizon area was measured at approximately 400,000 square kilometers.
Wow. Okay, which is comparable to the landmass of Sweden.
Exactly.
That is a massive increase in area, and therefore a massive increase in entropy.
The sources confirmed the total area definitively increased, which confirms Hawking's area law to what they call high credibility.
And what's so fascinating about this, beyond just the geometry, is the physics underneath it. The increase in area is governed by the mass of the final black hole, but also by its final spin. And the sources highlight that the spin increased, which tends to reduce the area relative to the mass, but the mass retention from the initial merger was just so high that the net effect was still a guaranteed increase.
It all balances out perfectly. This single measurement ties together general relativity, geometry, and fundamental thermodynamics. It shows this beautiful internal consistency in black hole mechanics. The laws are unified and they are robust. So we have it.
Definitive proof from the clearest cosmic observation ever recorded that general relativity is robust, the Kerr metric is accurate, and Hawking thermodynamics hold true in the strong gravity regime.
So, if the universe perfectly followed the rulebook you wrote for it, where does physics go from here? What's left to do?
That's the big question, isn't it? For decades, physicists have been in this desperate search for cracks in the armor of general relativity.
We know that GR, which describes the universe at large scales, has to break down eventually. It has to. Because it's incompatible with quantum mechanics, which describes the universe at the smallest scales.
And everyone hoped the extreme violence of a black hole merger, the strongest gravity known to exist, would be the place where we'd finally find the first deviations.
But the walls didn't crack.
They were reinforced.
They were. The result of GW250114 forces us to dramatically shift our scientific hunting strategy. We now know that if general relativity is going to fail, it's not going to be in the obvious fundamental Q&M parameters during a clean merger like this one.
So if we can't look for glaring errors in the Ringdown, where do we aim next?
Well, we have two primary avenues, and both require even more specialized analysis. First, as we discussed, we have to probe even higher Q&M overtones.
The even fainter, more complex echoes of that cosmic bell.
Exactly. Looking for microdeviations that might hint at new physics. But the second avenue is to look back at the in-spiral phase, the long, slow spiral of the black holes before they collide.
This is where we get into that discussion of post-Newtonian coefficients. That sounds incredibly technical, but it's super critical.
It is, but we can break it down. Let's use an analogy. Think of calculating the speed of an object.
Okay, classical Newtonian gravity, that has 0th order, or 0 PN. It works great for slow speeds and weak gravity, like calculating the orbit of Mars.
But not for black holes moving near the speed of light.
Not at all. For that, general relativity requires adding increasingly complex correction terms to the Newtonian equation.
So if you're calculating how fast a car goes, 0 PN is the speedometer reading. But if you're trying to calculate the orbital decay of these black holes, you need all the extra
Corrections.
Exactly. The first-order corrections, 1 PN, they account for basic relativistic effects. But the more subtle effects, like the energy being radiated away by gravitational waves,
they start appearing at the 2.5 PN and 3 PN order.
Okay.
And these correction terms, the post-Newtonian coefficients, they have to have very specific values, usually 0 or 1 if general relativity is perfect.
And what did GW250114 do for this? Because the signal was so clear and it lasted for a long time, the in-spiral went on for many cycles, and the detectors of GW250114 allowed scientists to set the most stringent bounds yet on these higher order PN coefficients that determine the gravitational wave phasing during that in-spiral.
So we constrain the values of these correction terms more tightly than ever before.
Yes. And essentially we didn't just confirm GR, we constrained the room for alternative theories to even exist.
So if some new proposed theory of gravity suggests a slightly different value
for, say, the 3 PN coefficient,
Then GW250114 likely rules that theory out because its prediction falls outside our new tiny error bars.
this is the real implication then. The goal has shifted from discovery to bound to the limits of our current physics.
Precisely. We are now using Einstein's success as a high-precision filter for everything else. For example, there are these things called scalar tensor theories, which propose a fifth force of nature.
Right.
Testing those requires measuring these really subtle PN deviations. And GW250114 just made that test much harder for those theories to pass.
It's the ultimate confidence boost in our cosmological understanding. And we also have to remember that the technology needed for this level of precision has immediate real-world benefits.
Absolutely. The engineering developed for GW detection requires ultra-stable mechanical systems and, crucially, ultra-stable laser light sources.
I mean, the level of laser stabilization you need to measure a proton scale movement over 4 kilometers is just, it's phenomenal.
It is, and the sources point to commercial spin-offs, like a company called
VM Photonics GmbH.
Right.
They produce ultra-stable laser light based on technology that was derived directly from the demands of LIGO. And that laser technology is now used in other high-precision measurements in advanced metrology, high-tech manufacturing.
So it's fundamental physics driving tangible technological advancement.
Exactly. So we found perfection. The geometry of the black hole is perfect Kerr. The ringing is perfect spectroscopy. The thermodynamics are perfect, aerial law compliant. If the theory is unshaken, even by the loudest cosmic event we've ever measured, the adventure hasn't ended. It's just gotten way more focused.
And that is the essential takeaway. The challenge for future physicists is now immensely high. They can't look for easy cracks in the theory anymore.
No.
They have to use the phenomenal precision of results like GW250114 to set the most aggressive bounds possible on every single alternative theory of gravity. This perfect success just raises a profound and provocative question for
you, the listener, to mull over as you go about your day.
And what is that question?
If general relativity and the fundamental rules of black holes are proven unshaken even by this
unprecedented clearest observation of a cosmic smash-up, what kind of cosmic events or what level of microscopic precision will it finally take to reveal physics beyond Einstein? We know the rules work perfectly
hope this deep dive into GW250114 has given you a profound appreciation for the level of statistical rigor and physical clarity that went into this monumental confirmation. Thank you for sharing your sources with us for this deep dive.
Keep digging for those subtle signals and keep challenging the rulebook. We'll catch you on the next deep dive.